Welcome to Why the Universe is Quite Disappointing, Really. I've had an unexpectedly large number of subscribers to this new YouTube channel, and all I can say is that I'm delighted to welcome you both back to episode 3. My social media advisors have told me that the previous videos were a bit long, and if I wanted to get more viewers, then I should make them a bit shorter, you know, the sort of length that a young person might watch all the way through, which I'm told is something like 2 minutes. Well, I can't actually do that. I can't get all the wonderful scientific knowledge that I possess into 2 minutes. I'd need at least 5 to do that. But I would, what I'm going to do is try and make these videos a little bit more concise. So I hope you'll bear with me on that. Another thing that I want to do in this episode is to branch out a little bit in a couple of ways. First of all, I'm going to deviate a little bit from astronomy and physics, which I've been talking about so far, and venture into the field of biology. Now, of course, I'm not a biologist, I'm an astrophysicist, but hey, this is YouTube. Since when did people have to know what they were talking about when they're on a YouTube video? The other thing that I want to do is, because I've been recording all of these just in my little flat here in Maynooth, I thought we'd broaden our horizons a little bit and I'd go and do an outside broadcast. So without further ado, we go over live to our man on Maynooth University campus.
Thank you, Brian. As you can see, it's a bright sunny day here in Maynooth as I stand here in front of the famous Stoit Hall. Behind me you can see the lovely trees. That particular tree behind me is a yew tree, which is one of the oldest trees in Ireland, if not the oldest tree. Almost 800 years old. That tree is often called the Silken Thomas tree, after Thomas Fitzgerald.
Get on with it!
Oh, okay. Well, using this vantage point and my acute powers of observation, I can report that the leaves on the trees and on all the bushes, and indeed the grass behind me, are all green. And with that, I return you to the studio.
Is that it? Hardly worth the effort, really. But at least we've established that trees, the leaves on trees anyway, and on bushes and grass and lots of other plants are green. Now, everyone knows why those plants are green. It's because they have within them a substance called chlorophyll. And chlorophyll is responsible for trapping light from the sun and using that to store energy in the form of sugar, a process known as photosynthesis. Now, if you actually know a little bit about astronomy, you'll find that very strange. And I'll explain why in the next sequence. A graph that shows the spectrum of the radiation produced by the sun. You can see that the sun radiates at a wide range of wavelengths, all the way from short wavelengths in the ultraviolet to very long wavelengths in the infrared. The visible part of the spectrum is just a small part of that range. You'll see that basically it's a rather irregular shape, but if you look at the shape of the black curve, which is the best black body curve, as it's called, a rough approximation, you'll see to the radiation from the sun, you'll see that it peaks round about the green or greeny blue part of the spectrum, which is around 500, 550 nanometers or something like that. Now let's compare this with the light absorbed by chlorophyll, which I've already explained is responsible for photosynthesis in plants. If you look at the wavelength range on the bottom of this graph, you'll see that actually chlorophyll absorbs virtually no light in the range where the sun is producing most of its light, in the round about 550 nanometers. And that, of course, means that the light that's in that range, in the green part of the spectrum, is reflected rather than absorbed. So there you have it. There's virtually a complete mismatch between the colours, the wavelengths at which the sun emits most of its energy, and the ability of chlorophyll to absorb that energy for future use through the process of photosynthesis. Now, of course, plants do survive. They survive very well. Here in Ireland, it's called the Emerald Isle. It's so lovely and green. But the point is that it's not a very efficient process because their minimum efficiency of the plants is precisely where most of the energy is around. With a little bit more effort, plants could have been much more effective at trapping light from the sun and using it. We might have even better plants than we have now if they were a bit better designed. They wouldn't be green, of course, because they wouldn't be throwing away and squandering the most abundant source of energy in sunlight. So I just flashed up that picture of the spectrum of light from the sun to remind me that I should really be talking about astronomy, not biology. But I'm going to move back to astronomy by having one last parting shot at biology, this time human biology. So I've already explained that the sun produces most of its light in the green range of the spectrum, but the sun doesn't look green. Moreover, if you're interested in amateur astronomy, and you go out at night and look at the stars with a dark adapted eye, you'll see that there aren't any green stars either. There are generally red ones and blue ones, and the others look kind of white and sort of colorless. So why does the sun not look green if most of its energy is coming out in green? Or why do stars not look green? Well, the answer is that our eyes are defective. I mean, my eyes are pretty good, actually. These glasses are not optical, I just wear them for their delightful appearance. But the point is that the human eye has three receptors that are sensitive to different colors. Rather like a computer screen and how that renders colors, they basically have red, green, and blue sensitivity. And the one in the middle is green, sensitive to green light, and it's actually the worst of the three. It's less efficient than the others. And that means that if you have a mixture of light, even if the maximum is coming out in the green receptors absorb it less effectively. So it can look like there's an equal spread of colors, which is basically colorless. So we don't really see green things very well at all. They're probably well enough to get by and to evolve to where we are, but really, again, it's not that overwhelmingly good, to be honest. Our color perception in the human eye is all right, but it's not brilliant. So now I've had a go at plant biology and human biology. I suppose I'm now going to get biologists commenting on YouTube. But anyway, such is life. Oh, by the way, please keep your comments coming on the YouTube channel. It's great to get all those comments. Not that I'll be reading any of them, obviously.